All right, well, we're going to take a look at a review of something called Vertex Form, which you were introduced to in the previous lessons. And if you take a look up on the left here, there is some notation. Don't worry about this f bracket x. It's actually called function notation, something used in grade 11 content, but this is very applicable anyway. So you notice there's the letters in here that are commonly used, but they don't have to be the letters that you see here. They could be just about anything. So you could use the letters A, B, and C that is used internationally, but in North America we decided to go with H and K just to have something to remember about, and you'll see why in a moment. So the graph that you see is your parent y equals x squared graph, your parabola. The a value is 1. All right, so making this relation just y is equal to x squared because h is 0 and k is 0 at the moment. So as we know by now, if we change the a value greater than 1, you get a new parabola that is a stretched out version. So this pink one or reddish one is a stretched out version of the green one. So we call that a stretch by a factor of 3.2 in this case. And compressions happen when the a value is a little less than 1. So there's the red graph. Compressed, again, means relative to the compressed along the y direction. So relative from the green to the red, it's getting closer to the x-axis. If the a value is negative, you should know what happens. Correct. It's going to be a reflection. So as you can see, there's reflection, but also the a value is between 0 and 1, so it's a little wider than what you would have for the base or parent parabola. So to get that exactly the same width, it would have to be -1. So now this is an exact reflection. And if you make the a value bigger than 1, it starts to stretch away from the x-axis, and it's still reflected because the a value is negative. Okay, so it's just a quick little review here. The h value in this particular formula causes the graph to, look at that, either move to the right if it's positive or move to the left if it's negative. So nothing brand new there. We're just doing a quick review. And the k value keeps the same shape that you have and either translates up or translates down. So again, those are two different words. You can either say translate or move. Either one is fine. And of course, you can have a combination. Now, the reason why this h and k is very important is because if you look at the key point here is 0, 0, that's the vertex at the moment. So changing the a doesn't really affect the location of that vertex. So I can stretch this out. However, changing the h and changing the k does affect the vertex. If you look at the location of the vertex, it's 2.8, comma, -2.4. And that perfectly matches the h and k values that I've used in the sliders off to the side here. So it's a perfect connection between the the aspect of what the vertex is all about. Just going to close something really quick so I don't get interference. All right, so it's just a quick little review. And now we're going to just do some extension of that. Just again, some more review here. So in the handout that I provided for the class anyways, so again, just looking very quickly at some of the information. So this is just trying to get used to the notation. So there's the notation that you're looking at in terms of the items that we're going to focus on. So the a value. So when the a value is greater than 1, then you have a situation where the graph of the parent, y equals x squared, is vertically stretched by a factor of a. Okay. And if the a value is between 0 and -1, it's not stretched, it's compressed. Very good. If the a value is less than 0, then the original or base parabola, parent parabola, is vertically reflected. Okay. So I'll show you the completed blanks in just a moment. Just wanted to get through some of the key items here. So as we've already taken a look at, and let's go to a different color here. So for h value here, if the h value in this notation is positive, so if the algebra looks like x minus and then a positive number, all right, so that is going to shift the graph to the right. Okay. Oops, just trying to get this to move properly. It doesn't want to move for me. That's a bit better. Okay, well, you get the idea. I'll show you the solutions anyways. All right, and for the h value being less than 0, then it's going to go the opposite direction to the left. Okay, and lastly, as we've already seen, the k value in this algebra here. So this k value here, if it's greater than 0, there's the k value. So comparing the parent parabola, that is going to shift the graph up. All right, and if the k value is negative, so if this is a minus k in the algebra, then it'll shift downwards. So there's a quick little review of the items that we're taking a look at here. And there's all the completed language in there. So again, vertically compressed, if the a value is between 0 and 1, greater than 1, it's stretched. For the h and k values, the h value affects movement left and right, and the k value affects movement up and down. And for the vertex, so the vertex is defined just like I showed in that Desmos demonstration using these letters h and k. So even if h is positive, you put the number in there. If k is positive, you put the number in there. All right, so that's just a quick little summary. Now, transformation statements are ways of finding new coordinates on the graph. So that's what we're going to be using to do some graphing today, as opposed to just kind of eyeballing it. We're actually going to get some accurate things. So because the a value is something that causes a stretch in the y direction, so it affects the y value. So this stretching and compression affects the y value. So take a look at what's happening in the ordered pair. It's a multiplication of the y value times that letter a, whatever that number a is. Okay, and then also the shifting right or left, that is your h value. So left and right movement is along the x-axis. So that's why we have this algebraic notation of adding to the x. Okay, so even if h is negative, we're really adding a negative, which will be the same as subtraction, and that's okay. And then lastly, the up or down movement is for k, and up and down is along the y-axis, but it's not stretching or compressing, it's moving it, just shifting or translating. Okay, so the language can change, translate, shift, move, that's fine. But if you move something up and down, it takes that particular y value and either adds to it or takes that particular y value and subtracts to it. So when you combine them all, this is the notation that you're looking at right here. Is this one here. Just pick an appropriate color, there we go. All right, so this one right in here is the format you're going to be taking a look at in terms of using something called a transformation statement. All right, so that's a transformation statement. Some of these values, h and k, could be 0. I'm not going to have an a value of 0 because I would not have a quadratic relation at all. All right, so stating the transformations essentially relies on you identifying what the a, h, and k values are. So what you need to do is kind of compare it to the information that you have originally given to you. And just to make sure that you understand what we're talking about. So we're going to have a y. Oops. Sorry. There we go. Y equals a bracket x minus h close bracket. And then this will be to the power of 2. And then plus k. Being a little stubborn today. Okay, there we go. All right, let me just get rid of this little item if I can. All right, so you can clearly see that. Okay, So in comparing, what you're going to have here, let's get rid of that. You take a look at each one of these equations and you try to match up what you see with the algebra and then identify the A, H, and K. And then you use that information to come up with your transformation statements just like we did before. So in comparison here, the A value is in front of a bracket. You don't have a bracket, but the interesting thing here is you can always type in a matching equation if you'd like, y equals 2 bracket. So we're keeping the 2 there. Now, if we're supposed to have an x minus something, power of 2 plus 3. Well, if I want to make these two equations the same, what do you think I have to use for this letter h in here? Correct, it's got to be a 0, because x minus nothing gives me x, and that'll match this equation. So now I know that the h value is going to be 0 in this particular case. So I have an h equal to 0. It doesn't matter what order you write these things down. I know the a value is in front of that set of brackets, and that's a 2. And then your k value is on the end, and it's a 3. So all of these pieces of information are very important to figure out. And once you get that established, then you can use the transformation statement up above here. X plus h, x plus 0, ay plus k. And you repeat this process over and over again to find the a value for each one of these, the k value and the h value. Now, the interesting thing with the middle one, I'll show you the solutions in just a second, but just to talk about this one here. So this one's got a pretty good match. So it looks like the a value is -1. That's not too bad there. And then inside the brackets, now look at what's happening inside the brackets here. You have a situation where you've got this, just change the color here. So you've got this situation, you have a +1, but the formula has a -h. So how do you turn a minus into a plus? What kind of number does the h have to be? If you said negative, you are correct. So h has to be -1. All right. And then your k value is just that value on the end right here. 4. And again, once you have all these established, then you use your transformation statement and write your transformation statements down below. And then you repeat the process with this third example, and here's the results you should be getting. Now, I've also included some language in here just to make sure you get accustomed to that, okay? Because the question did ask to state the transformations and then write a transformation statement. So I was just giving you a brief overview. So this black portion up at the top is the stating of the transformations. A value is 2. So the original parabola has been stretched by a factor of 2. The h is 0, so there's no words to include there. And if the k value is 3, it's shifted up. And as you can see, I've just used this transformation statement down here. Where did this come from? It came from this generic formula up at the top, x plus h, well, h is 0, and then ay plus k, so ay plus k. And then you just repeat the process with the other 2 examples. Okay, so hopefully this will help you get through at least understanding this concept of using the letters A, H, and K and coming up with some transformations. Now the next portion is using transformations to graph. So this is exactly what we're going to be taking a look at here. Now again, it's a matter of using that piece of information. I'm going to just capture what I can here. See if I can make a copy, paste it down here. Okay, now, so I don't need all this information now. All right, so again, same situation. You do exactly the same thing as these questions up here. So you can state the transformations, So your A value here would be -1. So this is your A value. There is no H value. As you can see, it's just x squared. And then the K value is +7. So the only transformations you have are stretch by a factor of 3 because the A value is 3. The negative is a reflection, and then a movement up 7. Now, some extra language is included in here. So the parent, this is coming from, if you're not quite sure here, I'll make sure that you're sure. So the parent is always, whoops, let me just get that lovely in there, okay. So the parent is y equals x to the power of 2, always is. It's always your parent. And then the child is the graph that we have, or the relation we have up here, y equals -3x squared plus 7x. Okay? So that's what the child function would look like. All right, so again, in these brackets here, what you're doing is you're coming up with your transformation statements. But again, you have to identify the A, the H, and the K. So I guess I'll just clarify. So y equals -3x to the power of 2 plus 7 will be your child graph. And again, you're using your transformation statements, and you're just going to plug in the numbers to get the new ordered pairs and then plot your points. Okay, so just to show you how that works. So you have a reflection along the x-axis because the A value is negative. It's vertically stretched by a factor of 3 because A value is 3. Shift up 7, and there you go. So all you're doing is you're typing in, or you're writing in your transformation statements, just as you did previously in the other examples. And so this is going to be your x plus h, so there is no h value. So what you're doing is you're taking your x coordinates that are in the parent and writing them here and coming up with new x values. Now, if you're wondering where these numbers came from, they came from a substitution. So this is -3 times y, so -3 times the y coordinate plus 7. -3 times the y coordinate plus 7, -3 times the y coordinate plus 7, and so on. You might notice the ordering is a little interesting here. It's done because there's repetition. So there's repetition in the y values, there's repetition in the y values here. So once you calculate one of these y values, it's going to be the same for the other one, simply because you're using the same parent y value. Okay? So -3 times 1 plus 7 is 4, and that's going to be the same here. 4 times -3 plus 7 is -5, and it'll be the same here. You plot all these points, and that's the red graph that you see here, and that'll be the new graph. Okay? So it's just a matter of taking some ordered pairs, creating new ordered pairs, and creating a new graph. And then similarly, you can do that with this other challenge question. Sketch a graph that represents the height of the baseball. So you can go ahead and go through the same process, but that is quite a bit. So I'm going to talk about a quick way of getting through this next one. This is a word problem. So this is a more different type of question where you have to be a little bit more specific. So this other question B here, same idea, state the transformations. You have your A, your H is inside the brackets, and your K is on the outside. Create your transformation statements, come up with new ordered pairs, and graph. So this one would be stretched, a little bit thinner than the parent graph that you see here. Shifted to the left. Now, how do I know to the left? Well, because this is a plus value, and plus doesn't match the formula that we had with the minus. All right, so again, taking a look at this comparison here. So the H value must be negative, so it must have gone to the left, and then the K value is negative, so it must have gone down. So I should expect, and this is one of the interesting things here, you should expect the vertex to at least be what your H value is, in this case -5, and your K value to be -1. Oops, so that's automatically one spot. There's your H and your K. So you can automatically plot that point, and that should appear also in your table right here, because this was the vertex for the parent graph. And this stubborn thing just won't move. So I'm going to move it over here myself. There we go. Okay, so that's the original vertex for the parent graph, and this is the vertex for the child graph. Okay, and we can see that here. So again, to the left and down and stretch. So it should be a little thinner, gone to the left and gone down. And these are all the completed values that you would have as far as the transformation statement. So again, x plus h, but since h is negative, it can be x minus, ay plus k, and the k value is negative, so you can write it this way. And then again, you take all your x values, plug them into these little formulas, x minus 5. So take all these x values and subtract 5, get new x values. Take all these y values in the parent, multiply them by 2 and subtract 1, get new y values, plot the points, and you got your new graph. Okay, now getting back to the word problem here. So you can do the same thing. It's a bit more tedious to do that. If you're just looking for a sketch of the graph. Now, notice that there's not a lot of room here. So the relation you have is H is the dependent, T is the independent. You should be able to tell me what the vertex is. Because in this particular case, the vertex, I'm trying to figure out what's collected here, all right? Okay, sorry about that. So your vertex here is going to be, just going to slide this over a wee bit, sorry about that, is based on the h and the k. So the h is 3, and your k value is 19. All right. Now, what you should also kind of try to figure out is the y-intercept if possible. But if this is a parabola, which is going to be, and it's going to be opening in a downward direction, your a value is negative, and there's your vertex. So your vertex is at 3 and 19. So somewhere there. And this is a video tracking device recorded the height of a baseball. Now, when you hit a baseball, it's not up from the ground, so it'll have some kind of initial height, which we could calculate, but not really worried about it. But there's a very cheap sketch that you can work with to possibly come up with some information. So in terms of getting an initial height, this point that we didn't quite get over here, key thing here is knowing that initial height implies when your t value is equal to 0. So you have a formula. All you need to do is plug in the t value to get a 0. And lo and behold, show you the result here. There we go. So again, there's the simple little graph. The t value is 0. You replace the t with a 0 in your formula, and you find your height. And now it's asking, what is the maximum height reached by the baseball, and when did the baseball reach its maximum height? Well, your vertex gives you that information, because your vertex, keeping in mind this is a relation with your x value, but in this case we're using the letter t and h. So your formula has t for your independent, h for your dependent. So the t at the vertex is 3, and h at the vertex is 19. And if you look at the graph, the highest point on the graph is exactly your vertex. So your maximum height should be 19. And when does that happen? 3 seconds. Why is it seconds? Because that's the information that's given. So the maximum height is 19 meters at a time of 3 seconds. When you take a look at that in the vertex. At what time or times was the baseball at a height of 10 meters? Now, this is a little bit more tricky. So you have a formula here. So 10 is your height. Oops. So actually, let's move this up. So now you're given a height of 10. that's equal to -2 bracket t minus 3 power of 2 plus 19. So this is the equation you need to kind of solve for, because what you're trying to do is find out the time. So you need to solve for t in here. Not an easy process, but you have to use inverse operations. So remember, with inverse operations, it's the inverse of bedness. So you're looking for subtractions and additions, followed by multiplications and divisions, and then any exponents and brackets to use inverse operations. So the first inverse operation would be subtraction, because it's the opposite of what we found here is the adding. And then once we have that, so there's the subtraction, followed by, we have some multiplication, which is the -2. So we'll have to use inverse operations to get rid of the -2 by dividing. And then the last thing is you have exponents. Now, how do we get rid of a squared? Correct, it's square rooting. So if you take a look here, so we've gotten rid of the 19 from both sides by subtraction, the -2 by division. Now we have to use a square root. So we square root both sides, and you do have to have a plus or minus in here. And the reason is when you square something, whether it's positive or negative, you can get a proper result. Okay. And then the last thing is to get the 3 to move to the other side using inverse operations, and then solve for t. So you get 2 answers for t. Now, why does that make sense? Well, if you take a look at the graph, you're looking for a height of 10 meters. So 10 meters is probably somewhere here. Whoops, that's a little bit large. Let's do this. So 10 meters is probably right about there. Okay, oops. And you have 2 times. Okay, so the 2 times would be indicated on the graph here. So you should have a small time and then a larger time, and that's indicated right here. 5.1 seconds is the larger time, and then 0.87 seconds is the smaller of the 2 times. And then the last problem to take a look at, here you have factored form, and you want to rewrite this in both standard form and vertex form. Well, everybody should be familiar with the standard form part. That's just a distributive property. Okay, and then the vertex form we'll take a look at. So your standard form is ax squared plus bx plus c. So you're going to take your factored form and use distributive property to expand. And now to get it in vertex form, you need the vertex. So you'll notice the letter A is consistent in both standard and vertex form. So you have the A value given to you in the original. In the factored form, it's also the same. So your A value is 3. To find the vertex, well, you've done that before. You've found vertex from factored form by finding the axis of symmetry and then plugging that in to get the y value. So the axis of symmetry is 1, so there's your h value for your vertex, and then substituting in to get your y value for the vertex, that's going to be used as your k, and then you can write it in vertex form, and there you go in terms of the overall result in terms of vertex form. Okay, so hopefully this helps you out in understanding some of the concepts of graphing using vertex form and also moving from one form to the other.